Our next speaker this afternoon is Dr. John Galsworthy from RWDI, who's going to be speaking about new frontiers in the wind engineering of tall buildings. John is a principal of RWDI and is now their global leader for wind engineering and has worked on all sorts of very notable tall buildings around the world. So carry on, John. We look forward to it.
Great. Thanks, Roy. Good afternoon. It's quite a title, New Frontiers in Wind Engineering. It's actually, it's really an opportunity for me to speak about some of the techniques we developed at RWDI in the course of looking at super tall projects over the last half dozen years, and in one example going back maybe as many as 12 years. But I thought, given the session, and given that the conference is targeted to a more general audience, I thought I would, as well as Volker did earlier, talk a little bit about just why wind is so important for super tall, and just talk a little bit about what vortex shedding is, and why it is that super talls in particular, super tall buildings in particular, are so sensitive. I'll go through a few case studies that we've been involved with in participating in helping design teams shape buildings to mitigate that vortex shedding effect. And then go through a number of projects where we've developed what I call incremental steps. We've been involved with testing at relatively large wind tunnel scales at a facility in Canada at the NRC in Ottawa. We've started to employ computational fluid dynamics, not only as a design tool, but also to look at the limitations of the tool. And Ahmed Abdelrazak mentioned some of those things this morning as well. With super tall buildings, we found that traditional criteria really aren't enough. So we've had the opportunity and need to really look at motion criteria for tall buildings in a very specific way, and I'll show through one case study what we did in that case. And then finally, advanced meteorology. Advanced meteorology is something we've first deployed on the Burj Khalifa, and at present we're actually working on that a little bit in more detail on another project. And then finally, I'll end off with just a few ideas that we have, and we're sort of bouncing around the office on what we can participate in or help the field develop for ideas for the future. So starting off, why is wind important for super tall buildings? Here's, of course, the Kingdom Tower that we heard about this morning from Adrian Smith, and we've had the good fortune of working on that for the last little while with them and Thornton Tomasetti. But if you look at wind, even drag loading, it's the dominant overturning load at the foundation. And so whatever you do to help the project in terms of the second point there, the crosswind, the drag load is still the dominant aspect of the lateral load. But there's something unique about slender structures and this vortex shedding, that it's the longer periods of slender structures, and then combine that with stronger winds at the top of the building. Those two aspects bring the critical velocity for vortex shedding. I'll define that in a second. But it brings that into the design range. And that's something that has to be complicated and best efforts made to mitigate that. So just Volker showed it earlier, a great example of vortex shedding at lab scale. Well, it happens at all scales. This is actually vortex shedding in the wake of a mountain. It's a terrific flow visualization in clouds. We have of course, wind moving this way, and you can see a very nice organized vortex street. So there's periodicity in that. So you can see that the vortex shedding sheds, or the vortices are shed at a rate, and that creates an oscillating side force. So in schematic form, if we look at vortex shedding and how it affects different shapes differently, I've drawn here about as basic a shapes as we can consider, one being a circle, one being a square. And if we have the same velocity and the same crosswind dimension, then the wakes of those two shapes are going to look quite different because of the Strual relationship. So the Strual is the constant for each shape in that equation that Volker shared with us earlier as well. But if we look at this equation expressed in this way, we have that the frequency of shedding in the wake is given by that Strual relationship. And so the organization or the spacing of the vortices are reflected in that shape. And so if we look at some speed where that shedding matches the natural frequency, that defines the so-called a critical velocity. And again, for super tall buildings, because that frequency is quite low, the natural frequency is quite low, as well as the wind speeds at elevation are high, then it brings that critical velocity into the design range. And so that affects not only acceleration responses, serviceability responses, but also loads. And just to emphasize there that the shedding frequency depends on the shape. So you can use those aspects in strategy shaping for wind. So this is an example why RWDI does not get into architecture. But these are sorts of things that we can look at and help identify as just potential ideas. So we can look at treating the corners. The corners actually, as much as they control the rate, they control the strength of the shedding. We can look at tapering or setbacks over the height of the building. Of course, you saw the Kingdom Tower example. But that as well helps to change the rate of shedding over the height of the building, changing the shape or changing the cross-section, that is, or porosity, or if we look at the industrial chimney example with strakes, that's something that we can try to incorporate in some buildings. So the first example that I know where this is really tested out in a lot of detail at RWDI, there's certainly examples from going way back, but the most famous example that we were involved with was about 12 years ago or so. And we looked in the design of Type A 101 at a number of different configurations. And through that effort, we were able to modify the base moment, resulting in a reduction of about 25%. And if we look at a more recent example, one that I was involved with at RWDI, is the Ping An International Financial Center, one of KPF and Thornton Tom Steady's buildings. Dennis Poon, who's in the audience, he's going to be speaking about that later, this project later in the conference. But this is a project that took some of those ideas into account. When you look at if you look at these corners here, we have a changing corner detail over the height of the building. And if we look at a couple of different cross sections, then at the corner detail helped to reduce the strength of the vortex shedding, and then that corner detail in fact changed over the height of the building. So as it went up, it had a changing effect. And actually that project, the vortex shedding effect was actually quite benign for a building of its height. It's about 660 meters tall. One more locally that we were involved with was the 151 tower in Incheon. And this was one where without mitigation, the responses were actually quite strong in terms of acceleration. So we participated in a program of looking at quite a number of different options, just to show a couple of different ones here, where we looked at both porosity at the top as well as openings along the edges. And this is more closely to what the final version looks like, which is quite agreeable to the architect, John Portman. But just in diagrammatic form, what that was able to achieve, starting from the original version to something closer to the final, we had a reduction in the base forces by about 40%. And then on Burj Khalifa, you've heard about both from Peter and Bill Baker and others, just how important the wind tunnel program was to the project, both in shaping orientation of the prevailing wind. I mentioned earlier some of the wind climate studies, And that was a project where we looked at the sensitivity to Reynolds number as well. So we got into considering what was the mismatch of Reynolds number. That's something that you just can't scale properly in a boundary layer wind tunnel. And so when we do a test at, say, 1 to 500 scale, which most wind tunnels operate in that range, we had to look at what the consequences of that were to the full-scale structure. And that idea we took forward on the Shanghai Center as well. It's a Gensler designed tower that everybody's aware of. So we had the normal testing program. In fact, we went through quite a complicated and detailed testing program on that, looking at different degrees of rotation, similar to what Professor Tamura showed earlier. But what I'll focus on here is the Reynolds number aspect. So that because we have the curved surfaces, those curved corners, then we were unclear whether or not testing at 1 to 500 scale were actually giving us numbers that were indicative of the full-scale structure. And so we went to a much larger scale, and I mentioned earlier that's this is the 9 meter by 9 meter wind tunnel at the National Research Council in Ottawa, where we tested at a Reynolds number more than a order of magnitude larger than what we could accomplish in our facility near Toronto. And what we did there, it's maybe difficult to see, but you could see rings of pressure taps. So we did pressure measurements on that at high frequency, and were able to pull out of that sectional force coefficients. So just show some results from this. So shown here is in red is the high Reynolds number result, in blue is the lower Reynolds number result. There's two things that we actually uncovered in this. One, that the drag coefficient, or the drag loading, was actually overestimated in the smaller scale test. And you can see that here in the data, where we've got the way the pressure coefficient changes. We actually have reduced negative pressures, reduced magnitude pressures in the wake, which indicates and is consistent with lower drag. But what we maybe weren't anticipating going in, but we also included in our recommendations ultimately on the curtain wall system, was that at the higher Reynolds number, we actually measured higher local pressures. And so that was something that we had we learned from that set of experiments, or set of testing. And that wasn't quite uniform over the whole tower, but certainly at the top of the tower where we had lower turbulence, and turbulence does have the effect of smoothing out some Reynolds number differences. But at the top of the tower where we had lower turbulence, so smoother flow, we saw these sorts of differences from the small scale to the large scale. We also applied that basic technique, or the high Reynolds number testing, to the Nikhil Tower, Woods Bagot, with Cantor Scenic. And in that case, the project was put on hold partway through. We were also intending in that project to do a larger scale aeroelastic test. But here we have the section test. So we have in this case, it was a prismatic tower, more or less, with some changes at the top, obviously. But because it was prismatic, we went to a two-dimensional section test, and looked at the comparisons, and we also carried out a similar type of test at the smaller scale. And for those of you with an aeronautical background or a bluff body aerodynamics background, understand the cylinder quite well, so this is sort of a meaningful plot to you. But in general, it shows the different set smaller scale tests, the 1 to 500 or maybe a little bit larger, in our facility in Toronto compared to the facility in Ottawa. So we got a reduction in drag coefficient, a measured drag coefficient, by about 20%. That wasn't uniform for all directions, but this was the worst wind direction for loading. We also observed a reduction in the strength of the overall shedding. So that's characterized by the fluctuating lift coefficient. So at smaller scale, we had somewhere in the range of 0.45, and then at the larger scale, higher Reynolds number tests about 0.35. So again, a significant reduction there. And then in the Struhl number, the difference wasn't quite as large, but one thing about Struhl number, which is the rate, a small difference, this is just for example, a square would be sort of in this range between 0.12, 0.14. A circle is typically in the 0.2 range. So we saw, say, about a 0.205 compared to about 0.19 or 0.195. And that doesn't seem like a big difference, but one thing to point out about Struhl number is that your end design loads are proportional to Struhl number squared. So even small differences in Struhl number can lead to significant differences in your ultimate or the design loads that one looks at. Now also on the Nikhil tower, because it was two-dimensional, and because in this particular case there was a number of configurations that were on the table, and it was difficult to achieve a rapid succession of testing because we had to build essentially a separate model for each configuration. We looked to CFD and using large eddy simulation, and we thought it a good use of the tool. Given that it was a 2D application, you could generate your simulation in relatively quickly as opposed to a full 3D simulation, which has its own challenges. And let's see if this works. It worked before. So we were able to do these simulations for the different options and look at the various different beneficial characteristics. And so we looked at a number of different configurations where we had changes in this opening, which allowed more flow through the center of the cross section and ended up reducing the overall strength of the shedding. Those are things that were done in advance of some of the other testing in order to guide a decision. And it was never meant as a replacement. I think Ahmed Abdelrazak mentioned that earlier today as well, that CFD is not there yet as a tool to replace the wind tunnel. And in fact, I think I'm safe to get through my career where it won't. But it is an effective tool, and the trends were certainly identified. So it was a good tool in that case. The Chicago Spire is Calatrava design, as everyone knows, again, the Thornton Thomas Eddy building, but we looked at a number of different configurations of the spiral, the angle on that helix that went up. But there was something about this particular project that challenged us in our thinking, and that was the role of higher modes and something that we had to deal with in the project. So just looking at the sort of generic flexural modes, the first harmonic and then the second harmonic. The first harmonic had a period of 17 seconds, and the second harmonic had a period in the range of 5 to 6 seconds. So each of those modes are within a range of period where the wind quite easily excites a building. So it's at the sort of very close actually to the peak of the energy in the spectrum, peak point of the spectrum. But it also that was another room. Yeah, okay. But it raised the question for us: what the heck do we do with criteria that are in place? And we had to look at what are the limitations of not only criteria as applied in North America, which are at that point 10-year return periods, but I think we even had to look beyond 1 year, which is AIJ and ISO. And the reason for that is because of the long period, we actually had quite high accelerations at about the 1 month. And so we had to look at that aspect. Again, the role of the higher modes increased the accelerations quite a bit as opposed to just looking at the fundamental modes alone. And what we did in that case, just before I move on to another aspect, just to point out the implications on the building as a whole. So if we look at the traditional method up to that point or shortly before that point of looking at only the fundamental modes, we would be predicting in red here the number of people that would actually might feel that acceleration and register a complaint. But if you look at looking at the higher modes as well, it brought in significant motions down the building. The consequence there is that the building is much more highly occupied, more dense in its population. So the likelihood of getting complaints with a higher population is higher. And so that's something that had to be taken into account. And so we engaged a facility actually out in Newfoundland. This is a simulator just designed to train ship captains in navigating through harbors and other situations like that. But because the periods we were looking at, 17 seconds, are similar to a rolling ship, it actually worked out quite well, and we were able to simulate reasonably well the motions that we were predicting. And if you've been in a ship simulator before, you know that you can actually project on the outside walls some sort of visual cue. So we actually put the downtown Chicago on the screen. And so people in our multi-million-dollar furniture there, but did a decent enough job of simulating. So we had chandeliers, we had the different elements that indicate motion. Just quickly, I'll go through some of the applied meteorology that we've been working on. The main motivation here is that when we're looking at very tall buildings, we have to address uncertainty in our wind engineering assumptions. So if we're looking at a conventional atmospheric boundary layer, then that's the model shown in the lighter red. But we're dealing with information that's registered at 10 meters above the ground, and we're making decisions about a kilometer in the air. So we want to take that into some consideration. So we've looked at WRF modeling, which is essentially weather forecasting in reverse. It looks back in time as opposed to ahead in time. And we're actually engaged in a study just at the moment looking at that, but also looking at some of the other tools and some of the uncertainty that's there. So one idea that has been put forward is to look at balloon data, but there's the issues with balloon data and that it's not generally released during the strong wind events that we want to capture. But there are some things from the balloon data that you can see that the velocity with height takes on a very different character for some type of events, particularly thermal-driven events or something around the boundary layer close to bodies of water. So using WRF tools, we can actually go back in, as I said, in a hindcasting mode and simulate, better understand what the profiles are and what the implications are to the project. So I'll just end on this slide with a few ideas of what I think can be improved on in wind engineering and the way wind engineering tools are included in design. If you were in the session this morning where Brant Kletta, Chuck Beesjack of Skidmore, Owings & Merrill were talking about the Busan Latte Town Tower. It's in Busan. It's about a 30% increase in wind speed, but a factor of 2 in wind loading compared to a tower here in Seoul. And so in that case, it was a strength-controlled tall building, which is unusual. Tall buildings were always thought to be stiffness-controlled. And so that, in conjunction with some of the things that are happening in America and will eventually be reflected in the IBC in terms of ultimate design, I think that's something where we can look to improve how our studies, wind engineering studies, can be reflected. So it brings up questions of what the appropriate level of damping is. Alex mentioned that in his last presentation. Given that, wind engineering has always been elastic. What are the consequences of allowing perhaps a handful of inelastic cycles through the design event? I think the tools, the data is there from our studies in order to reflect that in analysis. And then finally, looking at the implications on reliability and whether or not a project-specific load factor calibration or reliability study in general, I think would be a good step forward. So with that, I'll stop.
Well, thank you, John. We'll a lot covered there, so I'd be surprised if we don't have a few questions from out on the floor. All right, while you're thinking about it, maybe I'll chuck in with a question first, because I suspect Peter isn't going to ask you too many difficult ones, which is looking at your high Reynolds number testing that you did, comparing it with your smaller scale testing. The obvious thing, I'm sure you had some kind of a mismatch in the turbulence characteristics between the two wind tunnels and the two scales. How did you determine what proportion of the differences was due to Reynolds number differences and what proportion was due to the turbulence characteristic differences?
Well, we took some care in setting up the flow field. So you're right to point out that there are turbulent differences. There are differences in the turbulent characteristics. So when we're doing section model testing in general, we look at that. So we don't say if it's 10% turbulence intensity at the top of a building, we wouldn't simulate 10% in the section test. And so we did that both at the high Reynolds number and the low Reynolds number. So it's more looking at the basic aerodynamics of it.
Professor Tamura? Let me just wait a moment for the, yeah.
Related to your question, the Reynolds number, power 6 is still lower than the real situation. So how was the conclusion of your not conclusion, so how did you decide the design value based on the two different Reynolds number? So the real situation may be power 7 or 8, or I don't know, but...
Yeah, I showed it on the results for the Nikhil Tower, but not on the Shanghai Center, where there were a number of velocities looked at. I'm not actually, Peter might be better to answer on the Shanghai Center, but there was a plateau reached on the Nikhil Tower, and the other thing Nikhil Tower had was significant roughness. So you wouldn't have to get to say 10 to the 7 to reflect like you would on a smooth circular cylinder.
Okay, so we another question from Dr. Kim there.
There is some differences in pressure coefficient different according to the difference of the Reynolds numbers. In that case, how did you compensate the design wind load considering the differences?
How did we compensate?
How did you compensate the design wind load evaluation because of the differences of the coefficient?
We did reduce, so based on the high Reynolds number for the Shanghai Center, we were able to reduce the overall loading to some degree. I don't think we didn't go as far as what the data said we might be able to go, though.
In dynamic situations, it can be possible. Maybe the vibrations can be reduced in 20% in case that the coefficient is reduced 20%. Is it right?
So if the drag, if I understand your question, so that if the drag were to reduce 10%, then the overall drag loads, including the dynamics, they reduce by 10% as well. Yeah.
I think that looks like we've run out the questions, unless I'm going even more blind than usual. So thank you very much, John, for a very interesting talk.